Hello. So today, what I'd like to do is to talk about the third type of reaction category. The first one, of course, was precipitation reactions. The second was acid-base reactions. Now we're going to look at what are called oxidation reduction reactions. So this is section 4.4. There are a couple of other videos that you can refer to. Links are given in Blackboard. And these are oxidation reduction reactions. Now, oxidation reduction reactions are often, we don't really call them that. We call them redox reactions, REDOX, for reduction oxidation. And I'll abbreviate reactions as RXN, okay? So these are redox reactions. These are the reactions that are responsible for the greatest energy transfers in chemical reactions. So when you see an explosion, a chemical explosion like dynamite or TNT, or the burning of natural gas, or chemical batteries, lithium-ion batteries, these are all reduction oxidation reactions, redox reactions. They all involve essentially one reactant transferring electrons, one or more, could be one, could be two, could be three, generally not more than that. Once you remove 1, 2, 3 electrons, it's hard to take more electrons off of a species. And so the electrons are transferring from one atom to another. So this, for example, could be a copper atom. So I'll write Cu for copper. And often it's an ion that it gets transferred to. So this might be a silver ion, for example. And so when that happens, the electron is just hopping from one atom to another. And so when that happens, the copper now has a charge. Now it's an ion, right? And now the silver is neutral. It's an atom because it has that extra electron in there, right? Okay, so let me go through just real quickly the idea of the atom, the structure of the atom, right? The copper atom has 29 protons in the nucleus, and it has 29 electrons around the nucleus. We'll talk more about that later in the course. The silver atom has 47 protons, right? You get that from the periodic table. My floor over here, right? So you just look up the atomic number. So the silver ion has 47 protons because it's positively charged. That means it has one fewer electron, so it only has 46 electrons. So that's why it's positively charged. Once that electron hops from the copper to the silver, well, that doesn't change the nucleus at all. This still has 29 protons and this still has 47 protons. But now the copper only has 28 electrons, right? You lose one electron, okay? And now the silver ion has an extra electron, so now it's got 47 electrons, and now it's a neutral atom, right? So you see there's no charge here, it's neutral because it has the same number of protons and electrons. Here, it's a cation, right? Because it has more protons than electrons. The electron is the species that is able to migrate from one reactant to another. And this can happen with atoms and ions, but it can also happen within molecules. Very complicated molecules can involve the transfer of electrons. Okay, so these are redox reaction, moving of electrons from one species to another. Now, notice how electrical charge is intimately connected to this idea, right? So, you know, electrons are negatively charged, right? They have an electrical charge. The charge of an electron, I'm going to write it as QE, it's by convention, it's negative. Ooh, I don't know. Mistake there. 1.602 times 10 to the negative 19 coulombs. Okay, and that's typically abbreviated with a C. So negative 1.602 times 10 to the minus 19th C for coulombs, okay? The coulomb is the unit of electrical charge. It's the SI unit of electrical charge, okay? Now, what I'd like to do is note that because charge is what we would say quantized, like we don't have charges that are less than this, a half of that or a third of it or anything with the electron and the proton. Typically what we will do is then we will say that the charge of the electron is just the smallest it can be, but it's negative. So we just say it's -1. And then the charge of the proton, which is the same as the electron, just the opposite charge, we just say that that's +1 because we can't really divide these charges up any smaller. It's not technically, that may not be true. There's these particles called quarks, which have smaller charges. But for us, for chemical processes, the smallest charge we can have is this value right here. So we'll just call that -1 and we'll call the proton +1. Okay. So there we go. So that's a little intro in there. Now, what I want to do is I want to talk a little bit about what are called oxidation numbers. So this is a way of keeping track of electrical charge. Okay, oxidation numbers. And one of the things that you're going to be doing in the homework is assigning oxidation numbers as your little exercise to assign these numbers. Think of the oxidation number as analogous to the electrical charge of the species. What we're going to do is we're going to think of a substance. So for example, water. We're going to think of it as individual atoms, all of which have charges, and we call those charges oxidation numbers. So in what we'll see is that we'll say, hey, the charge of the hydrogen atom is +1, and the charge of the oxygen atom is -2, right? So we're going to go through that right now. Now, in reality, they don't really have those charges, but it's useful for us to conceive of them as having those charges as we look at redox reactions, okay? We'll get more into the idea of atoms not having these charges in chapter 8, but for right now, we'll think of each atom as having some sort of charge, either 0, +1, -1, so forth and so on, okay? So think of the oxidation numbers as being limited. These oxidation numbers can be positive or negative or 0. So they could be, for example, -3 or -2 or -1 or 0 or +1 or +2 or +3. So notice with oxidation numbers, we write the sign first, then the number. We don't write the number and then the sign. When you're doing charges in a species, for example, sulfate, SO4 2-, you put 2- up at the top as a superscript. For oxidation numbers, we put the sign plus or negative, and then we write the number. And then each atom is assigned an oxidation number. So this is assigning, right? We're telling these atoms what their oxidation numbers are. So the first step is, I'm just going to give you a table here of values. The first one is fluorine. Fluorine, and again, actually, let me be careful about this before I actually give you the individuals. We're talking about now compounds and polyatomic ions. So the oxidation numbers that I'm going to go over with you right now are referring to compounds and polyatomic ions. So here's the rules. Fluorine is -1. Okay, and that is pretty much invariable. It does not change. In any compound or polyatomic ion, fluorine is -1. Oxygen is -2. And there are exceptions to this. And one of the exceptions is if it's in a compound with fluorine. Okay, so if it's in a compound with fluorine, it turns out that's not true. Okay, the other exception are what we call peroxides. So a peroxide is a very unusual species, but it's not unusual. I shouldn't say that. It's a species that exists. We interact with it. So this is the peroxide ion. The peroxide ion has a formula of O2 negative 2, O2 2 negative, okay? In this case, oxygen, I'm going to write it in parentheses, is -1. Okay, in the case of fluorine, it's a little more complicated. But I'm just going to write it. Let me actually put this in brackets so that you can sort of see. Okay, so oxygen is -2 unless it's with fluorine. And then, or if it's in the form of a peroxide. If it's in the form of a peroxide, it's -1. Okay, hydrogen, +1. Again, there's an exception here. And the exception is really one, is what we call hydrides. So in this case, the hydride H is -1. Okay, so if you hear that, hey, it's a hydride, then you're going to assign the value -1 to the hydrogen. If you hear it's a peroxide, you're going to assign -1 to oxygen. Any other compounds or polyatomic ions, hydrogen and oxygen are +1 for hydrogen and -2 for oxygen. Again, remember, when I write the oxidation number, I put the sign and then the number, right? The value. Okay. So there you go. There's the first three. Now, the halogens. So these would be chlorine, bromine, and iodine. Notice I'm not putting in fluorine because I already discussed fluorine. Oops, sorry. I already did fluorine. These ones are -1. Okay. Now, there is an order of hierarchy in this. The order of hierarchy is that fluorine is in a compound or polyatomic ion will always be -1. Oxygen, notice that there's a couple of exceptions. Hydrogen, notice there's an exception. And then you have the halogens. Okay, so the order is important. This rule never gets broken. This rule gets broken a little bit, a little bit. These ones can get broken more frequently. Okay, there are more exceptions to those. The alkali metals, which are lithium, sodium, potassium, rubidium, and cesium, +1. So notice very often the oxidation number is the same as the charge of these ions, right? For example, chlorine, yeah, the charge is -1. Well, it turns out the oxidation number is very often -1 as well. Same with the alkali metals. What about the alkaline earth metals? Well, the alkaline earth metals, those would be beryllium and magnesium and calcium and strontium and barium, +2. Again, put the symbol for this, put the sign and then the number, okay? So not unusual there. Very often the oxidation number is the same as the charge, okay? Now, there's a few others, but I want to kind of, if you have these, you're in pretty good shape. Here's what I'm going to say now. Again, these are all numbers we're just assigning. We're saying, like, when you see something, you assign it that number, right? That's what it's given. Okay, you're essentially encoding that each atom with an oxidation number. So I'm going to give you a couple of rules here. One rule is compounds are neutral. Okay, we know that compounds are neutral. They don't have electrical charge. The sum of the oxidation numbers equals 0. Okay, that's another way of saying that they're neutral. All of them added up be 0. So for example, -2 and +2 adds up to 0. -3 and +3 adds up to 0. -3 and +2 and +1 add up to 0. The sum of all the oxidation numbers in a compound has to be 0. Okay. What about polyatomic ions? The sum of the oxidation numbers equals the charge of the ion. So for example, the sulfate ion, SO4 -2, the sum of all the oxidation numbers of those atoms in the sulfate ion has to be -2. You add them up, it's got to be -2. Sulfur plus 4 oxygens has got to add up to -2. 3. Elements have oxidation numbers equal to 0. So an element is 0. So if you see in a substance or a chemical equation, it says iron reacts with, or iron is produced. Iron is an element. It's got to be 0. If you're looking at a combustion reaction, methane plus oxygen is an element. O2 is an element, right? It's an element, so it's 0. So elements are always 0. So anything on this periodic table is 0 unless it's in the form of a compound or a polyatomic ion. Okay. Monatomic ions have oxidation number equal to the charge of the ion, just like polyatomic ions. But these are simpler, right? So for example, if I say a lithium ion, Li+, well, that's not an element because it's an ion, right? You have elements and you have ions. The ion, the charge of the ion, which for lithium being in the first column is +1, that would be its oxidation number. So many of these, you can figure them out very, very easily. Okay. And, for the most part, that's it. That should get you through 99% of these problems or 98% of these problems. I would recommend writing all these down in a way that looks clear to you and having them accessible so that you can use them. Okay. Save that right there. And let's take a look at a problem. Okay, some chemical reactants are listed in the table below. Complete the table by filling out the oxidation number of the highlighted atom. So that would be the atom that's in red. Okay, so let's take a look at this one. Bring this over. There we go. So you can see that a little bit better. Okay, so see how in each one of them, one of the elements is in red. So here's an oxygen, here's a hydrogen, here's a potassium, and here's a carbon. So 3 of these are really simple. One of them you have to work on a little bit, but here's the deal. The peroxide ion is the only well, actually, there's 2 exceptions for oxygen. One is if it's combined with fluorine. So this is the hydroxide ion, right? You remember this from acids and bases, OH negative. That's not fluorine, so it's not that exception. It's also not a peroxide, right? Remember, peroxide is O2 2 negative. There's no O2 2 negative in there, so it's not a peroxide. So that means oxygen is -2. So you just write -2. You got your answer right there. Very simple. There's a rule about elements, right? H2 is an element, right? It's one of the 7 diatomic elements. So elements are 0. So there's your rule right there. So that would be 0. This is potassium, K+. It's a monatomic ion, right? One atom. That's what monatomic means. One atom ion, monatomic ion. This is called a potassium ion, right? It's an essential nutrient, a micronutrient for us, right? So potassium ion, K+, monatomic ion. What's the charge? +1, right? Yeah. So your oxidation number would also be +1. Now, this one down here is a polyatomic ion. It's not a compound, right? It has a charge. The difference between a polyatomic ion and a compound is typically, well, a polyatomic ion means many atoms as an ion, right? Polyatomic ion, or at least 2 atoms and an ion. So it's a charge. So what we said was polyatomic ions, the sum of the oxidation numbers is equal to the charge. So that means the hydrogen's oxidation number, the carbon's oxidation number, plus all 3 of those atoms there, all 3 of those oxygens. So all 5 atoms together, right? 1, 2, 3, 4, 5. They all have to add up to -1. So what you do is you treat it mathematically. Our rule about hydrogen, +1. Our rule about oxygen, -2. We know all of those atoms. We just don't know this one, but we know they have to add up to -1. So you've seen that in algebra, right? Like I know this value, I know that value. The third one I don't know, but I know they add up to some value. Very, very simple arithmetic. So let's take a look at this one. I'll show you. So this is, by the way, called the bicarbonate ion. For those of you that are biology majors, you've got to know this one. Or if you're a chemistry major, you got to know this one. Also referred to as hydrogen carbonate. Bi is the older word, but we still use it. Sodium bicarbonate, right? Baking soda. So not hydrocarbonate, hydrogen carbonate. Hydrogen carbonate ion. Okay, HCO3. So here's what we know. There's your charge, polyatomic ion. So -1 equals hydrogen, which is +1. So let me actually, I'll just do it this way. +1 plus carbon. We don't know what carbon is. I didn't give you a rule for carbon. Many of the elements, there's no rule. You figure them out from the other ones that you do have rules for. And then you've got 3 oxygens. Each oxygen is -2. So I'm going to write it this way, 3 times -2, right? So you've got 3 oxygens. Each one is -2. You've got 1 carbon and you've got 1 hydrogen. They all have to add up to -1. Polyatomic ions, they add up to the charge of the ion. Compounds, they add up to 0. Okay, so just go through it arithmetically. If I subtract 1 from both sides, I get -2 equals carbon plus 3 times -2, right? I just just subtracted 1 from both sides to get this 1 over to the other side. Now, right? C minus 6. Why? 3 times -2 is my -6. Now let's add 6 to both sides. So -2 plus 6 equals C minus 6 plus 6, right? I added 6 to both sides. And so what do I get? +4 equals C plus 0 plus 4 equals C. So notice here carbon is +4. So if in red, that red element of carbon, we would say it's +4. You can go back and check it. Hydrogen is +1, carbon is +4. Each oxygen is -2. So if you're adding 3 of them, that's -6. Does that add up to -1? And it does, right? This is +5. This is -6. That's equal to -1, and you've got it. Okay, so go through your algebra for those types of problems. Very good. I have a couple of other examples of that when you go through the older videos, ones from last time. Okay. Let's see. Let me show you one more. I want to show you one that has a transition metal. So here's one, vanadium oxide. We'll go through this real quick. So notice VO, solid, that's a compound, right? There's no charge. It's not VO negative or VO positive, it's VO. So that's a compound, so they have to add up to 0. So this one's easy, right? Oxygen is -2. Vanadium's got to be +2, right? +2 and -2 add up to 0. So V is +2. This is a monatomic ion, I negative. It's not an element. It has a charge. That's not an element. So monatomic ions, the charge of the ion is the oxidation number, so -1. We just did this one. H2O. Well, this is not H2O2, hydrogen peroxide, just H2O, water. So hydrogen's +1, oxygen's -2. Just use the rules, okay? So again, the usefulness of having that table, fluorine, oxygen, hydrogen, the alkali metals, the alkaline earth metals, and then the halogens, all of those. Okay, so there you go. That's assigning oxidation numbers. Now that's actually an important aspect of this chapter. So make sure that you're getting good at that. The next issue I want to look at is recognizing oxidation reduction reactions, because now we've looked at 3 different types of reactions that are different, but you can sometimes get them confused. They look the same. You've got these chemical symbols and all of that, but they're different. So let's go through here. Okay. So this is all about determining oxidation and reduction. Actually, before I go through this one, I want to give you a little bit of a background on this, of how we determine this. We're going to do it essentially based on oxidation numbers. Okay, that's why we learn the oxidation numbers. So notice there's 4 equations in this problem set. Some of them are redox reactions, some are not. Probably just looking at it, it looks to me as though all of them are. It looks like all 4. Well, no, it looks like looks like they're all redox reactions. So if you find out that neither of them, nothing is oxidized or reduced, then you just select this one over here on the right. But it looks like they all are. But so let's go through it. I'm going to talk a little bit here about oxidation and reduction. And there's different lectures on this, so feel free to look at those. So oxygen versus reduction. Okay. So in principle, the idea is the following. Let's not worry about what atoms we're talking about, so I'll just color one in. These are different atoms, different elements. In general, the idea is this. If an atom transfers electrons to another atom, right, loses the electrons. So this one is the loss of electrons. Could be 1, could be 2. Okay, let's make it 2. Okay. Loss of 2 electrons, right? Loss of electrons is called oxidation. Okay, so that's one way to look at it. Loss of electrons is oxidation. Okay. This atom here is gaining electrons. So this is the gain of electrons. This is called reduction. Okay, now what I would do is memorize that. Loss of electrons is oxidation. Gain of electrons is reduction. There's a couple ways to remember it. One is Leo goes grr, you know, a roaring lion, Leo. Loss electrons oxidation, loss electrons oxidation, gain electrons reduction. Okay, so Leo the lion, remember Leo the lion. The other way is oil rig, or another way is oil rig. I think there's a third one that I forget. Oxidation is loss of electrons, reduction is gain of electrons. Okay, so whichever one loses the electrons got oxidized. So, you know, this one was oxidized, was reduced. Now, how do you tell in a chemical equation, though? It's clear from this picture that that's occurring, but how do you tell from the chemical equation? You use oxidation numbers. And here's how you do it. If you lose an electron, your charge will become less negative and more positive, right? Think about it. If you are neutral and you lose an electron, you become positively charged. You become more positive. On the other hand, gaining electrons makes you more negative, less positive. So if you're -2 and you gain an electron, you now become -3. So in general, here's what happens. You look at the equation and you look at the reactants. A, B, C, D, right? Reactant A plus reactant B gives you product C plus product D. Sorry, it's hard to see. That's a D over there. Okay. So let's say this A and C have the same element. Let's say they have oxygen in them. If the oxygen atom becomes more negative, that means it gained electrons. So that's reduction. If, on the other hand, the oxygen becomes more positive, then that's losing electrons, that's oxidation. So look at each element. If an element becomes more negative, then that's reduction. If an element becomes more positive, then that's oxidation, right? Because again, if you lose electrons, become more positive. That's oxidation. Leo goes Gur. Okay, that's as simple as that. So what you have to do is find the highlighted element. So it could be an oxygen, it could be a carbon. Figure out what its oxidation number is on the reactant side. Figure out what it is on the product side. If it became more positive, that means it got oxidized. If it became more negative, it became reduced. Okay, that's as simple as that. So let me show, let's come back over here. And most of these you can't really tell unless you really kind of go through it, but there might be sometimes occasionally a way to do it. So let's take a look at the first one. This one, I think we can sort of do it quickly. It's only the highlighted one we're looking at, right? So they're just saying, did it get oxidized, reduced, or neither? So see how that's hydrogen in water? We already did the oxidation number for water, right? It's in a compound. Hydrogen is +1. We didn't even have to do any arithmetic. We just go back to that table. Hydrogen is +1. So here's +1. Here it's an element. So it's 0. So it went from +1 to 0. Now be careful. If something is positive and now it's not positive, that means it became more negative, right? If I go from +3 to +2, that's becoming more negative. So that means you're gaining electrons. So that means that the hydrogen gained electrons. It went from +1 to 0. That's reduction, right? Keep it in mind. That's reduction, became less positive. All right. So the hydrogen got reduced. The way we would refer to that, this is kind of the language we would use. We would say that in this reaction between carbon monoxide and water, the hydrogen atoms in the water became reduced. They were reduced, not became reduced, but were reduced. Okay. Let's take a look at this one right here. Now, this one's a little harder, right? We have like a polyatomic ion. We have a polyatomic ion. How are we going to figure out what's going on with the chromium? So I'll do that one on paper. Third one. This one we can do relatively simple. Element 0, right? Carbon is 0 in this case. But now think about it. Even if you don't go through the arithmetic, we know that oxygen is -2. And you have 2 oxygens, so that's -4. So that means the carbon's got to be +4, right? If this part is negative, this part's got to be positive. So it went from 0 to positive. 0 to positive is losing electrons, right? The more positive you become, the fewer electrons you have, right? Because the electron is negatively charged. So it became positive. More positive is oxidation. So we would say that the carbon atom was oxidized in this reaction. So we would select this right here. This one's a little trickier here, the copper sulfate, but it's not that bad. And I'm going to show you a little trick for how to deal with it to make it simpler. But strictly speaking, think about it this way. Here we know it's 0. It's an element all by itself. So the only question is it going to be positive or negative over here? It's got to be one or the other, right? Well, I guess it could be 0 also. But generally speaking, in compounds and polyatomic ions, we don't generally assign 0 to any of them. Sometimes it might work out there's 0, but we generally don't assign it that way. So this is either positive. So if this is positive and this is 0, that means it became less positive, became more negative, so that's reduced. On the other hand, if this is negative and it became 0, that means it lost electrons, so it got oxidized. Loss of electrons, oxidation. So we just have to figure out whether that copper is positive or negative. But use your intuition. You know that in compounds, if you have a metal and a non-metal, the metal is positive and the non-metal is negative, right? We know that. Don't forget that. Positive, negative, cation, anion, right? Look at this. This is copper sulfate. It's copper. It's an ionic compound with a metal. The metal is going to be positive. So positive to 0 means it became more negative. More negative means it gained electrons. That means it's reduction. Gain of electrons is reduction. And you can use that as well, because with this one, they're not asking you to actually assign the oxidation number. They're merely asking you to indicate, whether it was oxidized or reduced. So let me show you number 2 and number 4 here in a little more detail. Again, we're just worrying about one of the elements. Here's the transition metal chromium. Here's the transition metal copper. Oops. Sometimes I have to quit the share. All right, so let's try this one. Don't worry about coefficients in these problems. And you don't need to worry about the state of matter, actually. Remember, state of matter was important in the other types of reactions, but not with these ones. Not a big deal, not an issue. We're just trying to assign oxidation numbers. So I'm going to write this down. Okay, so for this one, it's the chromium. So I'm going to see if I can do this. So it's chromium. I guess that's the chromate ion. And then you've got the dichromate ion. Oh, man. I want to get back and do some work on this stuff in the lab. Very nice stuff. Okay, so it's the chromium we're concerned with, right? Okay, so here's how I'm going to go through it, more formally, just like we talked about. So when you're doing this, this is just how many of the chromates there are. So don't worry about the 2. It's not, that will be important if we want to know the number of electrons, because that 2, if we lose 2 electrons and there's 2 of them, then we lose 4 electrons. So in terms of counting electrons, it's important, but not in terms of identifying whether it gained or lost electrons. So ignore the 2s. Not important, or the 3s there. That's not important. The state of matter, of course, is important in reality, but we're not going to worry about it here. It's not like we're writing the net ionic equation in a precipitation reaction. So it's just the chromium. So here's what I'm going to do. Let's do the chromium here. So chromium, see if you can figure out as I write this what I'm doing. What did I do there? I just did the algebra. I said, look, this is a polyatomic ion, right? Polyatomic ions, all the charges, all the oxidation numbers, I should say. All the oxidation numbers have to add up to the charge of the polyatomic ion. So they have to add up to -2. So all I did was I wrote that in algebraic form. I said chromium plus 4 oxygens equals -2. And then I said, oxygen is -2, so chromium plus 4 -2s has got to equal -2. Okay, now you could do kind of some clever arithmetic here, but I'm just going to be kind of brood about it. Just sort of how I kind of do it. Step by step is how I do arithmetic, so I don't make mistakes. So chromium -8, right, equals -2. Add 8 to both sides. Right? Why am I adding 8 to both sides? Because I have -8 on the left side. So if I add -8, so if I add 8 to the left side, -8 plus 8 is 0. So that leaves me with the chromium. -2 plus 8 is +6. Remember, don't forget the plus. Got to put the plus or it's incorrect. So here it's +6. This is called, by the way, chromium 6. If you ever watched the movie, it's now old. I think the movie came out when I was in college. Chromium 6 was in this movie called Aaron Brockovich. who was a woman in California who was fighting a utilities company who was pouring compounds that had chromium-6 into the ground, which was getting into people's well water and was causing people all kinds of illnesses and cancer, killed people. So chromium-6 is a nasty element. We have to be very careful and keep it out of the environment, okay? But it's useful for very many things, so we still have to use it. So chromium-6 right there, okay? Now, let's come over here. Here, I'm going to show you this one carefully. There's 2 chromiums. Don't forget that. So 2 chromiums plus 7 times -2 equals -2. Okay? So again, polyatomic ion, so it's got to add up to the charge. If it were a compound, if it were just Cr2O7, it would add up to 0. So now, what is that? 2Cr minus 14 equals -2, right? 2Cr equals -2 plus 14. 2Cr equals plus 12. Cr equals plus 12 over 2, which is plus 6. And guess what? Chromium didn't change. It was neither oxidized nor reduced, which that's very interesting. So what type of reaction is that? It's not a precipitation reaction. It's not an acid-base reaction, as far as I can tell. I have to think about what kind of reaction that is. Is it a metathesis reaction? I'm not sure. But in any case, it's neither oxidized nor reduced. So this is not a redox reaction. Very interesting. It went from plus 6, it's still chromium-6. Okay, that's as hard as it gets, to be honest with you. So now let's do the last one. The last one was the copper. So copper sulfate. Again, I'm not going to worry about the states of matter for assigning oxidation numbers here. And then the element that they're interested in, oops, is copper. Okay, so now here, I told you there's a little trick. It's not really a trick, but it's just kind of thinking about it. We know this one is 0, right? Not a problem. That one is 0. It's an element, so elements are 0. The question is the copper. Now, again, we knew it's positive, right? Or it should be positive, right? Here's how you treat ionic compounds. You recognize that as an ionic compound, right? It's got a metal and a non-metal. You think of it as ions. You got the metal ion, and then you got the non-metal ion, right? Which is the polyatomic ion in this case. That's the sulfate ion. Recall back when I talked about precipitation reactions in section 1 and 2, 4.1, 4.2, that having those polyatomic ions can be very useful for you. I would recommend having a list of polyatomic ions, because then what you'll see is you'll say, oh yeah, ionic compound, metal, non-metal. That's the sulfate ion, SO4 -2. So now think about it. An ionic compound in this case is really just a monatomic ion here and another and a polyatomic ion here, right? It's 2 ions bound together. That's what an ionic compound is, a cation with an anion combined together so that they're neutral. So if this one's -2, this one's got to be +2. So you know it's positive now. So what happened? Copper went from +2 to 0. That's more negative. Okay, wrap your mind around that, right? It went from +2 to 0, so that's more negative. Think of your number line. If you're going from +2, here's your number line. Amazing, right? Stuff they taught you in the 2nd grade. One of the little secrets about chemists is that for the most part, we don't do arithmetic beyond the 6th grade. Maybe not even beyond the 5th grade for the most part, okay? But we do a lot of it, so it looks like we know our math, right? So the point is that you started at +2 and you ended at 0. So which direction are you going? Are you going positive or are you going negative? You're going negative, right? You're moving towards the negative. Negative is gaining electrons, right? So we're gaining electrons. Gaining electrons. Oil rig, right? Reduction is gain, rig. Okay, so that's reduction. And so it's interesting because we often think of metals as getting oxidized and non-metals getting reduced. And that's true in general, except if you combine different metals. So a metal might reduce another one or oxidize the other one. So the copper here is getting reduced. It turns out, I'm not going to go through it. Had they asked you to do zinc, you would find that the zinc got oxidized. There's a relationship, just like with acids and bases. Something is an acid, something is a base. If you don't have both, you can't have an acid-base reaction. Same is true with redox reactions. If something gets reduced, something has to get oxidized. Why? Come back to the idea of the electron, right? The electron's got to go from one point to another. So this one's getting oxidized, this one's getting reduced. You're not going to have one get oxidized and nothing get reduced, or vice versa. Okay. Close that one up, and there you go. Now, I do want to show you the idea of agents. So this is confusing it was confusing to me when I first started learning chemistry, this idea of something we call an agent. An agent is the same thing as a reactant. Okay. And historically, we call redox reactants agents. So we don't say reactant 1 plus reactant 2. We say reducing agent plus oxidizing agent. Okay. And then it's the same products. That's not different. But the terminology is one of the reactants is called a oxidizing agent and the other one is called a reducing agent. Okay. So here's the logic behind something, or here's one way to think about it. I didn't spell that right, did I? If something gets oxidized, it's the reducing agent. And if something gets reduced, it's the oxidizing agent. Okay, the logic behind this is the following. If what's happening here is this is getting oxidized, right? It's losing the electrons. This one's getting reduced. It's gaining the electrons. But the reactant, a reactant does something. A reactant reacts with something else. So what happens is the terminology is that if something is getting oxidized, that means it's losing the electrons and causing the other reactant to get reduced. This one is actively reducing this one. This one is oxidizing this one, right? They're doing the opposites to each other. So this one would be called the reducing agent. And this one would be called the oxidizing agent. And the reason that we like that terminology better than oxidized or reduced is, which we use that too, but the reducing agent, oxidizing agent terminology, the reason we like that is because we might say, wait, I have this substance and I want to take electrons from it so I can change it. So I need an oxidizing agent. I need something that can take the electrons from it, okay? Or maybe I have this and I want to put electrons on it. So I need to figure out, hey, can you go get me something that will put electrons on this species? So I need a reducing agent. So in the environment, certain substances tend to be reducing agents and they tend to be oxidizing agents. So here's, some of the, in terms of elements, these are a couple. Fluorine, oxygen, those are oxidizing agents. In fact, the terminology oxidizing means reaction with oxygen, right? So, or oxidized means reacted with oxygen. Those are oxidizing agents. Where are the oxidizing agents? They tend to be over here in the periodic table. F, O, Cl, N. Those are your oxidizing agents. Where are the reducing agents? They tend to be over here. Okay, the metals. The metals are more reducing agents. Now, it's more complicated than that. If you go on to take more advanced chemistry courses, you'll see more nuance in that, more details, and a more wide range of compounds and substances. But in general, the strongest oxidizing agents are these ones in terms of the periodic table, and the strongest reducing agents are these ones over here. Okay. But we often use polyatomic ions and compounds, and that complicates things. But in any case, let me show you a problem. Okay, here we go. Identifying oxidizing and reducing agents, okay? Is it a redox reaction? Which one's the reducing agent and which one's the oxidizing agent? Remember, agent means reactant, so don't put formulas for products on these. You shouldn't have to put the state of matter in there as well, or if there's a coefficient, you don't need that either. Just put the chemical species. So these are two agents here, carbon dioxide and water. So one, if this is a redox reaction, one of them's the oxidizing agent, the other one's the reducing, okay? If it is, but how do we tell? Now that's an interesting thing. What is a little tricky here is that you got to essentially assign oxidation numbers like we talked about. So I'm going to kind of go through this first one here and show you. Okay, so oxygen is -2. Oxygen is -2, oxygen is -2, oxygen is -2. So nothing's happening to oxygen. Hydrogen +1, +1, +1. Nothing's happening to hydrogen. The only question is, what about carbon? Carbon here is +4. You can go back and watch how we assign that. That's +4. Here, it's also +4. Okay, why? Each oxygen is -2, so that's -6. The hydrogen is +1, so that's -5. It has to add up to -1. So the only way that works is if this is +4. Okay, so both cases, carbon's +4. So that means it's not a redox reaction. If nothing changes oxidation number, it's not a redox reaction. Okay, so really I'm just using the rules of oxidation numbers. Let's look at the second one here. We did this one, copper sulfate. Actually, we just previously did that one, right? So copper, we know this is a redox reaction, yes, because we already figured it out. It is, right? Copper's +2 and here it's 0. Zinc now, zinc is 0 here, it's +2, because remember the sulfate ion is -2, so the zinc is +2. So let's go through this. Zinc went from 0 to +2, oxidized. If you get oxidized, you're the reducing agent, right? So the zinc is the reducing agent. Copper went from +2 to 0. That means it gained electrons. That means it got reduced. If you get reduced, you are the oxidizing agent. So the copper sulfate is the oxidizing agent. Just be sure you write down the whole formula. This whole thing is considered the agent, even though it's really the copper that's doing the reaction. Okay. Last one here. Carbon plus oxygen goes to CO2. Okay, well, the carbon is 0 here as an element. Here it's +4. So that means it lost electrons, which means that it got oxidized, which means it's the reducing agent. Remember, if you get oxidized, you're the reducing agent. You get reduced, you're the oxidizing agent. So carbon's the reducing agent. Oxygen here is an element, 0. Here it's -2 because it's in a compound. That's where we use our rules. So it went from 0 to -2. That means it gained electrons, which means it got reduced. If it gets reduced, it's the oxidizing agent. So there you go. So O2 would be the oxidizing agent. Carbon, C, would be the reducing agent. And there you go. That's how you do those. And that pretty much wraps up. There's one more type of problem, which I don't have time to go over. However, that problem is in a previous video. It's about the half reactions. So if you have difficulties with the half reactions, just refer back on Blackboard. It's in YouTube, right? But I posted chapter 4, all the videos, and so it'll be on that one. My next video will be on molarity and dilutions, which is the final topic of chapter 4. Okay, so look for that soon. Take care.